Okay, in this video presentation, I will be explaining about A-star search algorithm. A-star is a powerful pathfinding algorithm used in various applications from video games to robotics. This presentation will provide an in-depth exploration of its mechanics, efficiency, and practical applications. We will also discuss its advantages over other algorithms, making it a preferred choice for many developers. The ASR algorithm combines heuristic and cost-based approaches to find the shortest path. It evaluates nodes using a function that considers both a cost to reach a node and an estimated cost to the goal. This allows it to efficiently prioritize paths while exploring the search space. The main components of A-star algorithm includes the open set, which contains nodes to be evaluated, and the closed set, which holds nodes that have already been processed. The algorithm uses these sets to track progress and avoid redundant calculations, enhancing efficiency. The crucial aspect of A-star algorithm is the heuristic function, which estimates the cost from a node to the goal. A well-designed heuristic can significantly improve performance by guiding the search process. Common heuristics include Manhattan distance and Euclidean distance, each suited for different scenarios. The algorithm is widely used to various fields, including game development, robotics, and navigation systems. Its versatility and efficiency makes it ideal for real-time pathfinding scenarios, allowing for dynamic obstacle avoidance and adaptive routing in complex environments. In conclusion, the ASR algorithm is a robust pathfinding solution that balances efficiency and accuracy. As the technology adaptations of ASTAR will emerge, potentially integrating with machine learning techniques to improve its heuristic capabilities and real-world applications. Now we'll look at an example to learn more about it. Let us consider this graph, and we are going to perform the A-star search algorithm to this. So the start node of this graph is A node and the goal node is I. These are the heuristic values of each node, and the numbers which are present between every two nodes is the cost which will be requiring to travel from the given node to another. Here we'll be using the formula Fn is equal to Gn plus Hn, where Fn is the total cost that is required for traveling from one node to the another, Hn is the heuristic value, and Gn is the cost which is used to travel between two nodes. So we'll start the search algorithm. We start from the start node, which is A. A has a heuristic of 366. When we explore this A node, we'll end up in three other nodes, which are C, E, and B. And these will be the cost of traveling from A to C, A to E, and A to B respectively. So after looking at these three costs, we'll find we'll also consider the heuristic values of each of the three nodes. The heuristic value for C is 329, D is 244, and E is 253. When we add the cost of the paths, we'll end up in having C having a cost of 447, E of 393, and B of 449. Here they'll be here we have mentioned the cost of the node plus the heuristic value. This 140 is the cost of traveling from A to E, and 253 is the heuristic value of E. 75 is the cost of traveling from A to B, and 374 is the heuristic value of B. When we add the both values for every node, we'll end up with these three values, and we'll choose the minimum value among those three. As you can clearly see, E has the minimum value of 393. So we'll start exploring node E. When we explore it, we'll end up in two more nodes, which are G and F. Now we'll see the heuristic value of G, which is 193. Plus, we have to calculate the value of starting from the start node to G through node E, which is 140 plus 80. So we'll add both of these values, which are the heuristic value of G, which is 193 plus 140 plus 180, which is the cost required to travel from A to G, and we'll end up in 413. And when we look at node F, we'll be adding 140 plus 99, which is the path for, plus the heuristic value of F is 178. When we add 178, 140, and 99, we'll end up on 417. Now we look at the unexplored nodes of this graph, which are C, G, F, and D. And these are the costs required to travel from A to the respective nodes. When we have when we look at all these nodes, we can see that the minimum value belongs to node G. We'll proceed with exploring node G. Node G will end up in H. The heuristic value of H is 98. So we'll be adding 98 plus 97 plus 80 plus 140, which will be resulting in 415. It has only one node, so we'll stop with this. Now we look at the unexplored nodes again, which are C, H, F, and D. So when we compare the heuristic values, when we compare their total cost, which are 447, 415, 470, and 449, we can clearly see that 415 is the minimum value. So now we'll explore node H. Node H will result in node I. I has a heuristic value of 0 because gold nodes will be having the heuristic value as 0. So now we'll calculate the cost for A to node I. So we'll be adding the heuristic value, which is 0 plus 101, 97, 80, and 140 will result in having a total cost of 418. Now we can very well see that we have reached the goal node already. We will start our search with this and we'll end up in a cost of 418. So our path of reaching the goal node from the start node will be A, E, G, H, and I with a total cost of 418. This will be the final state of our graph. We have not reached the goal node, so our search will stop here. Now we look at the principles behind A star search algorithm. Optimality. A star is guaranteed to find the least cost path if the heuristic HN is admissible, which is it has to never overestimate the true cost to reach the goal. Efficiency. A star avoids unnecessary paths by focusing on the most promising nodes, balancing exploration and exploitation. Heuristic. The heuristic plays a crucial role. An ideal heuristic is considered for monotonic, meaning Hn will always be less than or equal to Cn, n plus Hn for any nodes n and n dash. Practical application and significance of A star search applications. Navigation systems. A star is widely used in GPS and mapping software to find the shortest route between two locations. Video games. For air pathfinding, A star allows characters to navigate obstacles and find efficient paths in complex environments. Robotics. A star helps robots plan paths to target, especially in structured environments where minimizing time or energy is critical. Significance. Optimality guarantee. Given an admissible heuristic, A-star guarantees the shortest path, making it ideal for mission critical applications. Admissible heuristics. In applications requiring real-time decision making, heuristics like straight line distance for navigation keep A-star efficient without sacrificing accuracy. The A-star search algorithm stands out for balancing optimality and efficiency, making it invaluable for practical pathfinding and navigation tasks. Thank you.